On the grandest scales, our universe runs on highly predictable rules. Gravity dictates the precise paths of massive objects like planets and stars. We see this same predictability in our everyday lives. Hit a billiard ball, and it follows a single, certain trajectory. It moves left or it moves right. It never does both. But shrink down to the microscopic level of quantum physics, and those rules break down. Down there, particles behave like fuzzy, smeared-out waves, capable of existing in two different places at exactly the same time. Albert Einstein spent his life trying to formulate a theory of everything, a single mathematical framework that could unite the predictable laws of gravity with this erratic quantum behavior. He never succeeded. Physicists still can't explain how a collection of erratic quantum particles produces the stable, gravity-bound behavior of a planet. This disconnect remains a primary barrier to a complete understanding of how the universe functions. Einstein rejected this quantum weirdness. When fellow physicists theorized that two entangled particles could instantly affect each other regardless of distance, he dismissed it as spooky action at a distance, arguing the universe simply couldn't work that way. In the 1960s, John Bell formulated a way to mathematically test this quantum entanglement. But for decades, actually conducting those tests in a physical lab was considered nearly impossible. Eventually, researchers did figure it out. Recent Nobel Prizes were awarded to teams who successfully proved entanglement in the lab. But those tests were done using photons, tiny particles of light. Light has no mass, and because it lacks mass, a photon cannot reveal how quantum mechanics interacts with the heavy physical pull of gravity. The paradox remained open. To solve that mass problem, a team deep underground at the Australian National University spent nearly 20 years building a highly specialized laboratory anchored directly onto stable bedrock. Most famous physics experiments, like the Large Hadron Collider, work by smashing particles together at high speeds and energies. The ANU team does the opposite. They need their particles to be extremely slow and extremely cold. The process starts by taking heavy helium atoms and cryogenically cooling them with liquid nitrogen. This strips away their thermal energy. Next, the atoms pass through a device called a Zeeman slower. Using an intense copper electromagnetic coil, it forcefully decelerates the helium from 1,000 meters a second down to a crawl of less than 100 meters a second. Stripping away all that heat and kinetic energy is the only way to stop massive atoms from acting like solid, predictable billiard balls. It forces them to drop their disguise and reveal their underlying fuzzy wave nature. Once the helium is in this ultra-cold state, the team uses precisely calibrated laser beams. Acting like microscopic cue sticks, the lasers push the atoms into an incredibly slow-motion collision. If they were normal objects, they would just bounce off each other. Instead, the atoms enter a state called momentum entanglement, dissolving from solid points into overlapping, smeared-out wave patterns. This smeared wave pattern constitutes a physical reality, a single atom moving along two entirely different trajectories at exactly the same time. It stays in this split state right up until the computer registers a measurement. That active observation forces the wave function to collapse, making the atom suddenly choose just one solid location to appear in. After recording thousands of these cycles over several weeks, the data confirmed it. This is the first definitive proof that heavy, physical matter, not just pure energy or light, can occupy two distinct physical locations at once. What separates this ANU experiment from decades of previous tests comes down to a single property. Helium atoms are heavy. Because they possess measurable mass, their physical state and momentum are inherently subjected to the gravitational pull of the Earth. By successfully sustaining quantum entanglement in massive objects, researchers have created an environment where two opposing sets of physical laws are forced to interact. They've isolated the exact threshold where the classical world of gravity bleeds directly into the weirdness of quantum mechanics. This brings us right back to Einstein's incomplete work. For a century, physicists have been trapped by a mathematical divide, unable to merge the formulas governing small-scale atoms with those governing large-scale gravity. Now, the data generated by tracking these heavy helium atoms provides a physical testing ground for theories attempting to bridge that mathematical gap. It's easy to look at this fundamental research and see only abstract concepts, but mapping the basic rules of quantum mechanics has historically been the direct precursor to our greatest technological leaps. Demonstrating that a heavy atom can occupy two locations simultaneously moves quantum theory out of the realm of speculation. It offers the concrete data needed to finally reconcile Einstein's gravity with the behavior of the microscopic world.